Start recording. So it's a pleasure to have Professor Luiz Nunes Oliveira here with us today. Professor Oliveira got his bachelor's at USP São Paulo in 1973, his master's in São Carlos at USP São Carlos 1975, and his PhD in 1980 in Cornell under the supervision of John Wilkins. After that, he went for 2 postdocs abroad, one at the University of California in 86 and 88, and at Ohio State University in 94 and 95. And since 1974, he's a professor at USP in São Carlos. And today, he's going to talk to us about orthogonality, catastrophe, snares, a bound state in the continuum. Professor Oliveira, thank you very much for agreeing to talk to us. It's a pleasure to have you here. The microphone is yours.
Thanks a lot, George. Well, this morning, George was helping me learn how to set up the presentation. And we tried a few browsers and found out that the only one that worked was Safari. And this seems fit because we're going to embark on a hunt for a bound state in the continuum. Okay, so, but let me first present my collaborators. This work is mostly the research of Luiz Henrique Jesse, mostly his PhD work, although we did some more research after that. And Antonio Ceridonio was also involved in this work. In fact, the original idea was his. Okay, so what I'm going to tell you is mostly due to what Luiz Henrique figured out. Well, let's see if we can understand the various terms in the title. And I'll start with the bound state in the continuum. When you are at kindergarten, you learn about the hydrogen spectrum. And it's something like what you're seeing here. You see that there are bound states, and then there's a continuum of extended states up here, and there's a threshold separating the two. And at that point, you might have thought that this is always true, that there is always a threshold separating the continuum from the bound states. Turns out that this is not true, and I'll give you a very simple example. So this example is for toy helium, not the variety that you have in your labs, but an imaginary kind of helium in which you have 2 protons and then you have 2 electrons, but the electrons do not interact with each other. They only interact with the nucleus. Okay, so the spectrum is very similar to what we have in hydrogen, except that the energies are bigger because you now have Z equals 2, and the energies go like Z squared. And in addition, now since you have 2 electrons, you can play with them. Okay, so one state I can have is this one on the left, and I put 1 electron at the 1s bound state level, and the other one is in the continuum part of the spectrum. Now it costs me 4 Rydbergs to lift the electron from the 1s level to 0, and then it costs me 2 more if I want to leave it here. So altogether it's 6 Rydbergs. Now I could also have a state with 6 Rydbergs by exciting 1 electron out of the 1s to the 2s state, and another one, say, to the 2p state, although it could be to the 2s state as well. Right? So In this case, you also have 6 Rydbergs. It's three Rydbergs apiece. Now, so this state, although it looks like a bound state, it is degenerate with the continuum states, right? And the important thing here is that this level has a very well-defined energy. And so this very well-defined energy is degenerate with the continuous part of the spectrum. So this is an example of a bound state in continuum. Of course, this configuration here is not an eigenstate of real helium. If you had real helium, there would be interaction between the two electrons, and this one could move down and use the remaining energy to kick this one up. So it would end up in a state like this, and you wouldn't even need radiation. Right? So this is an example of a radiationless excitation, but this is only for true helium, right? In this toy model, this is not possible. But I just want to mention to you that this excitation process is what is called the Auger. When this electron leaves and goes away, it's called the Auger process, even though it was discovered first by Lise Meitner, but because she was a woman, the name got associated with Pierre Auger, who discovered it later. Okay, that's the way things go, or went, at least in those days. But so this is a very simple example of a bound state in the continuum. And now we want to understand the rest of the title. So let me tell you a little bit about the Anderson catastrophe. And this is a very simple phenomenon, although it has very important consequences. This is something that Phil Anderson figured out over 75 years ago, in fact. Right? The idea is the following. If you have a solid, a metal, right? So you have conduction electrons here, and then there are valence electrons down there, maybe deep 4 levels, empty states up here, perhaps. And then suppose that for some reason, one of these electrons is kicked up to some other state, either here or some other level, which is out there. But the important thing is that it leaves behind a hole, and this hole has a positive charge that interacts with the conduction electrons. And so there's a potential which phase shifts the conduction electrons. So from the white kind of function you had, now you phase shift it to another one, which is slightly different. Okay, so there is a phase shift here. And what Anderson showed was that if you had many electrons in your system, then this state with the phase shift must be orthogonal to the original state, right? It has nothing to do with the way this electron is promoted. It has to do with the phase shift. As long as you have a phase shift, then, and you have many electrons, then the final state, the ground state of the final state will be, orthogonal to the initial state in the ground state. Okay, the 2 ground states will be orthogonal, and the orthogonality analytically is written like this. And here's the number of electrons you have in your system, and then delta is this phase shift. So this is a universal law, which will reappear in the future. So I ask you to pay attention to this number, which will show up later. Okay, but now what we want to get into our hunch for the bound state in the continuum. And for that, we need a model. And I'll start with, well, I'll show you a very simple model. This is a model that has been studied many times in the last 20, 30. Actually, the first time was 1985, as far as I know. But the model is like this. You have quantum wire, and then you have two quantum dots. Okay, there are different versions of the physical characterization, but the model is like this. A quantum model coupled to identical quantum dots by an identical coupling. And then there's a gate potential that controls the number of electrons in the quantum dots. Okay, so this is described by the simple Hamiltonian. Here's the conduction band. Here is the potential that you have applied to the electrons that are at the dots. In each dot, there's a repulsion U, Coulomb repulsion U, and then there is this coupling. Right? So this is an Anderson model with two impurities and a single conduction channel. Right? Nothing too complicated. On the contrary, it's very, 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 very simple. Now, when you have something like that, because these two sides are identical, you realize there is some sort of symmetry. And obviously, if I exchange side one with side two, the Hamiltonian will remain unchanged. And therefore, you have kind of a parity conservation here, because if you define a state, an even state as d1 plus d2 over the square root of 2, and an odd state as d1 minus d2 over the square root of 2, this is going to simplify your graph. Okay, so this is the parity, even, odd, and that is corresponding. If you were a chemist, you would call this a bonding combination, and this an anti-bonding combination, and that's the language I'm going to use. So A here stands for the anti-bonding, and B for the bonding combination. But you could also say even and odd; it's the same thing. All right. Now, so our Hamiltonian was written like that in terms of d1 and d2. But if you change to this basis, you don't change the CKs, but you change the Ds, and then you end up with a system that looks like this. You still have the conduction band. You haven't touched the conduction band. But now, instead of having two dots coupled to the wire, you have only one dot, only the bonding state is coupled to the wire, and the anti-bonding state is completely decoupled, right? That's because of this minus sign, because the combination here is positive for both dots. Okay, so this one is completely decoupled. This one is still coupled. In fact, this coupling is now a little stronger with the effect of square root of 2. That doesn't change much things. The important thing is that this one is decoupled. However, it's not completely separate from the system, because there is, because of U terms, there is some interaction between the A and B orbitals. So your Hamiltonian now reads something like this. You still have the conduction band. Now you have a term associated with the anti-bonding orbital here on the right. There's a term associated with the bonding orbital, which comprises both what's happening inside this dot and its coupling to the quantum wire. And then there is some sort of interaction between A and B. And if you want to see what these terms look like, here they are. Right? So let's start with the bonding term, which is a little easier to understand. If you look at the bonding term, it has some energy multiplied by the number of electrons at the bonding stage, a Coulomb repulsion, smaller one, U over 2, but just the same as you had before. And then you have this coupling. So if you look at the bonding Hamiltonian, it's just like a simple Anderson model. This hasn't changed. The only thing that has changed, the energy that has been renormalized, but the general form is still the same. If you look at the anti-bonding level, because it's not coupled to the conduction band, it's very similar, but it doesn't have this last term. Okay, otherwise it's an energy multiplied by number of electrons plus the Coulomb repulsion. And now, what about the interaction? That's interesting because the interaction Of course, the interaction it's about a bit more complicated. It's not a quadratic term, right? This term is quadratic, this one is quadratic, but this one cannot be quadratic. And it has two kinds of interaction. One is the spin-spin interaction between the spin in dot B and the spin in dot A, right? Notice the negative term. That means, that the interaction is ferromagnetic. So it tends to polarize the two spins to be pointing in the same direction. And here it's an isospin interaction, very similar to this one. Isospin, for those who have forgotten, isospin means something that's associated with the charge of the quantum dot. And it's a kind of a dual to the spin operator. So if you have the quantum dot doubly occupied, the isospin will be 1/2. If the quantum dot is vacant, then the isospin will be -1/2. And if it has one electron, the isospin will be 0. Okay, so this is, it follows SU2 algebra, just like the regular spin. So this term is very similar to this one, except it couples charge instead of coupling spins. Okay, we'll talk a little bit more about this then in a while. But okay, now this transformation to a basis with well-defined parity is by no means new, right? It's a standard procedure, and people in the audience have used them in different papers, right? So it's not a surprise that it has been applied to this very same model some time ago, right? Well, in particular, this is a paper that is very interesting. I really recommend reading it. It's by Gitko and collaborators, and was published like 10 years ago. And they look at this very same system. They have a slightly different notation, but it's exactly the same system. And they did numerical renormalization-group work, diagonalized the Hamiltonian, and looked at some of its properties. And they found out that there is a phase transition, right? In fact, this had been pointed out by Vojta and co-workers many years beforehand, about 10 years beforehand. But Gitko and collaborators really identified the region or the phase diagram for this phase transition. Right? So this is what they have. Look, they are using epsilon, where we are using VG. Well, the other symbols are very much the same. Oh, and they use an odd, where we were saying an A. Okay. So what they found is that there is a region in VG times U space. So if U is very small, for instance, you are around here. If U is large, you go towards the right. And here you're changing VG. And in this gray region here, the number of electrons in the antibody level is exactly equal to 1. Whereas in this region, this white region, it's not equal to 1. Okay, this is what they found. Their motivation to do this work was quite interesting. They had done, Gitko and other collaborators had done similar work back in 2007, 2006 on the same model. And they had found out that there was a phase transition. Now, sometime later, Beta Azzet's study of the same model showed that there is no such thing, no such phase transition. Right? They found out that things are more like this white region all over the diagram. And so the question was, what is right? NRG or beta ansatz? And so to settle this question, Gico decided to do some Monte Carlo calculation, and then his Monte Carlo calculation confirmed this fact. Right? So this meant that there was something wrong with the beta ansatz computation, and actually there is a phase transition. Okay, so this was back 10 years ago. All right. Now let's move on, and we are now decided to look for bound states in the continuum in this system. Okay, so let me start with a very simple reasoning. Suppose that u equals 0, right? Every place where I have a 0 here, green 0, I had a u in the previous slide. So if I let u equal to 0, the Hamiltonian will be just like that, with the u terms missing, as a result of which, in particular, this last term is identically 0. Right? Here, it's simpler, but the most important thing is that this is identically 0, which means that now there's no more coupling between A and B. And now the A level is completely on its own. Right? It's completely decoupled from the rest. Now, not only decoupled, but it's non-interacting with the rest of the system. So this is a true bound state. And if the energy is right, it will be in the continuum. So this is a bound state, can be a bound state in the continuum. Right? Now, this is something that was found out back in 1985. This research didn't consider quantum dots and things that was not common at the time, but they were doing working with a different arrangement, and they came to the conclusion that there would be a bound state in continuum in a system similar to this. Unfortunately, if you turn on the interaction, then this term will again mix these two orbitals via interaction, spin-spin interaction, isospin interaction, as a result of which you no longer expect to have a BIC, right? A BIC. For the case where u equals 0, you can check that you do have this situation by calculating the spectral density, right? Because remember, we have to search for the BICs with the view to showing the experimentalists how to identify this animal. And this, in practice, means that I have to think of some experimental technique that might do so. Now, photo emission is exactly what measures the spectral density. And if I apply photo emission to the system, I find out that, first of all, I can have photo emission from the A level or from the B level. And so that's why I have an alpha here. This alpha can either be A or B. And if I carry out this calculation, this is a simple model with u equals 0. I can diagonalize Hamiltonian analytically, and I can calculate the spectral densities for the A and B levels. And then I find out that for the B level, I have, for the bonding level, which is coupled to the conduction band, I find out that there is a nice Lorentzian with gamma. Gamma is pi rho v squared, where v is this coupling here. And there is a very sharp line associated with the anti-bonding level, right? Which means the anti-bonding level is a bound state in the continuum. And so this is the signature we want to see more generally, right? This works very well for u equals 0. But as I have pointed out, if u is not equal to 0, then there will be interaction here, and then this will not longer be like that, and I expect that this line will be broadened, which will mean that it's no longer a BIC, not a bound state in the continuum. Okay, so we want to see what would happen under those circumstances. So I let the U now be different from 0. And now I can no longer diagonalize this analytically, but I still can have diagonalize the Hamiltonian using NRG, for instance. Okay? Now, before doing that, however, it's very useful to notice that the commutator between H and the square of the spin associated with the anti-bonding orbital equals 0. This means that this quantum number associated with spin operator is conserved, right? The spin of the A state is conserved. That's the total spin. The Z component is not conserved, but the total spin is conserved. Okay, this is very easy to check. You have just to calculate. You have the commutator taking every term into account, and you find out that this is true. All right. Now this is very useful because it tells you that when I'm thinking about bonding or anti-bonding, or when I'm thinking about even or odd states, I can also think of the spin of the anti-bonding operator. Let's see how that works. Spin is conserved, right? So it can either be 1/2. This is a single orbital, so it can only have spin 1/2 or 0. Now, so it can be 1/2 or it can be 0. If it's 1/2, see you have one electron here, so the isospin is 0, the spin is 1/2. If you are in this situation, spin equals 0, there are two possibilities. Either this level is vacant, or you can have 2 electrons. Now, in either case, spin equals 0. In either case, the isospin is 1/2. The Z component is minus 1/2 here, is plus 1/2 here, but the total isospin is 1/2 in both cases. All right? And so I can say that states which have odd parity, because there is 1 electron in the anti-bonding level, have spin 1/2 at the anti-bonding level. And states which have even parity, because now I have no electrons or 2 electrons in the anti-bonding level, and this is the orbital, right? The anti-bonding orbital is the one that carries the sign. So if there is 1 electron, your many-body state will be odd. If there are 2 electrons, or if there's no electron, then the overall many-body state will be even, right? And this is associated with the spin. So you can say odd, or you can say spin equals 1/2. You can say even, or you can say spin equals 0. It's the same thing. Okay. Now, so this means that I can take the Hamiltonian and look at its spectrum and break its spectrum into 2 separate sectors. There's a sector where the odd state lives, where the spin of the anti-bonding level is 1/2, and there's another sector where the even states live, and where the spin is equal to 0. Okay, so let's look at the odd sector, and here is the total Hamiltonian. But in the odd sector, there's only 1 electron at the anti-bonding level, and so either this is 1, the other is 0, or the other way around. So this term is necessarily equal to 0. And the same thing is true about this term, because the isospin here equals 0. I don't know about the bonding isospin, but the anti-bonding isospin equals to 0, and so there is no such term. So you see, you have a Hamiltonian for the odd sector in which these 2 terms do not contribute. This term is still the same, but these 2 terms do not contribute. Now, if I now go to the even sector, now the spin equals 0 at the side, and the isospin equals 1/2. So now I have isospin interaction, but I don't have spin-spin interaction anymore. And so the bottom line is that the even and the odd sectors have different Hamiltonians, and hence they'll have different energies. Their spectra will be different, right? In other words, they're not degenerate. And so when I diagonalize the Hamiltonian, total Hamiltonian, I'll have odd eigenstates, I'll have even eigenstates, and they will not be degenerate, which means that the ground state in one of them is very likely to be below the ground state in the other. It could either be like I have it here, or it may be the other way around. Maybe this one will be lower and this will be higher, but they will not be the same, right? Except under very special circumstances, if I choose the parameters to make this one equal to this one. But otherwise, they will tend to be different. And this, when you do your NRG calculation, this comes out very, very nicely. Okay. Now, what I'm showing here is the ground state of the odd sector, right? The odd sector comprises all the eigenvectors which have odd symmetry, which have one electron at the antibonding level. And on this side, you have everything that has either vacant or doubly occupied antibonding level. Right? And so this is the ground state, and then you have excitations on top of that. Right? What's the ground state? The ground state will have one electron at the antibonding level, and then there will be excitations that you can have. There's something about the bonding level here, right? The antibonding level is a single electron in the antibonding orbital, but the bonding level, in this case, also has one electron in the bonding level. And then there are excitations on top of that. What are these excitations? Well, I can have particle hole excitations, and then those will grow up in energy, and then I'll have higher and higher energy states. Okay, since the bonding level has a spin, a single electron in this configuration on the left-hand side, there will be a Coulomb effect somewhere up here, right? It's an Anderson Hamiltonian, so there will be a Coulomb effect, and then we'll come to the ground state. And in the ground state, you have this electron, the bonding electron will be screened by the Coulomb effect. The conduction band will be phase shifted by pi/2, and everything else will be quiet. That's what you have at the very low energy. So in this region here, up here you can have things that are more complicated. Now, if you go to the even side, then things are different. Here, the antibonding level is either vacant or doubly occupied. Normally, it's a linear combination between these two. And then again, you can have excitation on top of that, right? And here too.
Luiz.
Yes.
May I ask a question?
Please.
Yeah. You are working at particle hole symmetric point all the time?
No, not necessarily. I can work there, but they cannot. Not necessarily. Right. I know. I'll give you two examples. One where we are at the particle hole symmetric point, and another where we're not at the particle hole symmetric point.
Okay. Thank you.
Right, thank you for the question. Right. Please, if someone else has questions, please ask them, because This is always very helpful. Okay. Okay, so this gives some light, shed some light on the phase diagram that Gitko detected 10 years ago, right? So what you see is, see, George, this is the particle hole symmetric point, exactly where the dg plus u equals 0. And so this, for this reason, this part of the diagram is symmetric with respect to this one. Okay. Now, what we have is that if you are around here in this region, the picture is like this. The spin 1/2 state is below, the spin equals 0 state is up there, and therefore the ground state has spin 1/2. The number of electrons at the odd, that is the antibonding level, equals 1. Right? Now, if you fidget with the parameters so that you leave this region, then what will happen is that these blue lines will move down with respect to the orange ones, and eventually they'll become degenerate. This will happen exactly here. And beyond that, the blue states will lie below. And that's why the number of electrons here is no longer equals to 1. It's a linear combination between 0 and 2, and it can be anything. So generally to be different from 1. Okay, over here, in fact, it tends to be closer to 2, and here it tends to be closer to 0. But so that's why you have different phases. So this is very easy to understand from this picture. Okay, now if we look at this figure, we can see something very promising, because you see you have a level here in which you have 1 electron at the antibonding level, and you have another level in which you have either 0 or 2 electrons at the antibonding level. And so if I carry out an excitation from this side to this side, I expect that the number of electrons in the antibonding level will change. And I might expect this to be a very sharp transition, right? Because you're going from ground state to ground state. This is an eigenstate of your system. This is another eigenstate. You're going from here to there. If you went from here to here, to the neighboring states, then here there are particle hole excitations, right? So you might say, well, here there are no particle hole excitations. Here there are particle hole excitations. So I cannot make a transition from this point to this point, but I can make a transition from here to here, right? If you're optimistic, then you would expect to have a very sharp line between these 2 points, and that would be a bound state in the continuum, exactly what we're looking for, right? So here, this looks very promising, but it's not what happens, right? I have to take this out. Okay, this is not what happens, because we have the Anderson catastrophe. Right? And so let me show you how this works. We have the same picture I had before, right? And here I can go from this level to this level using the antibonding spectral density that I mentioned in a previous slide. And I can go from here to here, use the bonding spectral density, right? Because the bonding spectral density does not has an operator that does not change parity, whereas the antibonding operator has the operator dA, which does change parity. Right? So we can probe either one of these 2 spectra, And here I have the results, the NRG results, which Luiz and Jesse produced. And what you see, first, let's look first at the bonding level. And let's look at this inset. And you see that spectral density on a linear scale, it has a very nice Lorentzian, just like the one I showed you for when I discussed the U equals 0 case. And then there's a very sharp line here, which, however, when you blow up the scale using a logarithmic scale, you see that it's not that sharp. Right? It has some width, and then you can identify this with the Kondo resonance. Remember, the bonding state is coupled to the impurity, and hence it will give rise to has spin, so it gives rise to a Kondo effect, and this is what we have here. Okay, and you can show that this line fits very well the Kondo spectral density, so there's no question about it. This is the Kondo resonance. Okay, now this is for the bonding level. Let's look at the anti-bonding level. And then the first thing I realize is that to reach the minimum energy, I have to pay a price. Right? There's a minimum energy that's necessary to be overcome before I come to the spectrum. Right? So if I look at the spectral density in this region, it will give me 0. No question about it. Right? So let's subtract energies from this minimum energy, which I call a threshold. Right? There's a threshold to be overcome before I can have transitions, spectral density, in other words. Right? And so I'm measuring the energy from the threshold. Now, the threshold is so small that in this inset here, it doesn't make any difference. Right? So, but it will make difference here when I look at the expanded scale. And what you see, so on a linear scale, is that you see is, again, a Lorentzian, but then there's a very, very sharp line here. This is no longer Kondo effect. There cannot be a Kondo effect here because the spin is equal to 0. But there is something, and again, optimistically, you might think this is BIC, but it's not. Right? And this is proven by the main plot. The main plot shows that if you look at spectral density around here, it follows a power law with exponent 1/2. Right? Here is the threshold energy from which I'm subtracting the energy epsilon, and then I'm following this. This fits very, very nicely this curve with exponent 1/2. In fact, this is what you expect, because under these circumstances, there is work that was done by Doniak and Sunik back in 1970, right, when most of you hadn't been born yet, and they looked at the problem of photo emission from a metal, and they figured out that when you have photo emission, which is exactly the kind of experiment we're talking about here, you expect the spectral density to go like d over epsilon minus epsilon t to the power 1 minus 2 delta over pi squared. Now here we are at the symmetric point, right? And therefore, if you are at the symmetric point, the phase shift must be equal to pi over 2 at low temperatures. So the phase shift is pi over 2. This ratio gives you 1/2. The squared is 1/4. This is 1/2. 1 minus 1/2 is 1/2 is exactly what we have here. Right? So this is precisely what you would expect. And you see that this number, delta over pi, comes up again. This minus delta over pi comes up again. Remember when I told you about the Anderson catastrophe, I asked you to remember this number, right? This is the exponent that Anderson found out. So this is the signature of the Anderson catastrophe. So what this means is that the conduction electrons, right? Because you're looking here at energies that are not equal to zero. You're looking at that close to the minimum energy here, but above it. Right? So this means that you're looking at the electron-hole pairs. And this expression tells you that electron-hole pairs rob energy, rob spectral weight from the ground state. Okay, the ground state is down here. Let me go back to the previous slide so that we can see this better. The ground state is down here, and you would expect that there would be 100% transition from here to here. But that's not what happens, because these electron-hole pairs, they steal spectral weight from the ground state, right? As a result of which, the ground state becomes orthogonal to the other one. The overlap here is zero, so there is no spectral density at zero, at epsilon equals epsilon t, the minimum energy. Instead, there is spectral density over here, right? So this is the smearing that we were talking about at the title of this presentation, right? That is the state that should be a BIC has been smeared over the electron-hole pairs, right? And so this is what happens when you have a typical situation here at the particle-hole symmetry points. What about other points? Nothing very different, right? So here's another calculation. Now we're not at the particle-hole symmetry point anymore, right? If we go back to Zitko's diagram, the first calculation was here. There's this particle-hole symmetric point for u not equal to zero. And now we are doing something around here, right? Now, if we do the calculation in this region, then what we see, again, a power law, right? This, look at the orange line, forget about the blue one. I'm going to skip the inset because I'm just about at the end of my time. But you can see that if you look at the orange line, the other one is similar. So if you look at the orange line, the exponent has changed. It was 1/2 in the previous slide, and now it's 0.495. Not a big difference, right? What happens is that here, the phase shift is no longer equals to pi over 2, and so this number is slightly different, right? Not big deal, right? So it's almost the same thing. But now the question comes, and I could have done this also in the particle-hole symmetric case. The question comes, can I get rid of this effect, right? Can I somehow recover the BIC, right? There is a BIC hidden in this diagram, or in this one, right? Which is waiting to be released. And I need to do something to get to release it, right? To uncage it. Right? And what we have to do is simply to make the two phase shifts match, right? This one has a phase shift close to pi over 2. This one, in which there's no counter effect, has a phase shift close to 0. So there's a big difference between the two phase shifts. If I shift the phase on this side without shifting the phase on this side, I can make them identical. In that case, this will disappear, right? And this exponent should be equal to 1. And something I'm not telling you here, but the proportionality factor decays in proportion to sine of delta squared. So if delta goes to 0, the proportionality factor will also go down to 0. And this is what this blue curve shows you, right? What the calculation was done here with the potential, a gate potential, applied now to the conduction wire. And that gate potential phase shifts the phase of the even levels, does not change the phase of the odd levels, and therefore, as you can see here, if I apply stronger and stronger potentials, the blue level will have a phase that will change from 0, it will go up, 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 and eventually it will match the phase, which is close to pi over 2, the phase of the odd levels. When it does that, exactly at this point, the difference between phase shifts will be 0, as a result of which you expect this exponent to go down to 1 and the prefactor to be 0. It's very difficult numerically to read exactly the right k, which will assure that. But if you have the potential, if you try something close to it, and here it is, 1.723, then you can see that the power law has changed a lot. In fact, it's gone down to d over epsilon t minus epsilon to the power 1, which is what you would expect for delta equal to 0. And the prefactor hasn't quite gone down to 0, but if you look at this curve, you can see that this one has dropped a lot, right? So it's on its way to having value 0. It will be impossible numerically to reach this value 0, but it will be close to 0. So we are having a limiting process, which is going to the situation where the phase shifts are identical, and then there are no longer excitation to these states, and instead the excitation will be from this stage to this stage, right? And that's that will be a very sharp transition. There will be a line that will merge down here, the delta function line, and this will be the BIC we were looking for, right? So here's my summary, and if you have questions, please please ask them, because I'll be very glad to try to answer.
Thank you very much. Thank you very much, Luiz, for the very nice seminar, very didactic. So this seminar is open to questions now. Edson, a question?
Thank you, Luiz, for very nice talk. And it's amazing how you find very interesting physics, and something that has been studied, including myself. I tackled this problem not looking at the BIC, but Kondo effect in this model. But my question seems to be naive, but I think since you are here, it will avoid me spending time thinking about that. So how can you apply a gate potential that shifts only the phase of the even and not the odd, because presumably you change both, right? Sorry for the noise here. My kids, my son's here. So
okay. Maybe they have enjoyed the talk as well, right? Okay, Edson, very good question. Right? That's something I should actually have mentioned. The thing is that when you apply, the way you apply this gate potential is apply it to the conduction band, right? That's simple enough, experimentally, let's say. Now, what that potential does, it tends to affect the even and the odd sectors. But because there's a counter effect in the odd sector, the phase shifts are much less sensitive than the even sector, where there is no counter effect. Right?
Okay.
So, because when you have the counter effect, the phase shift wants to be close to pi over 2, and you can do whatever you want. Don't never get too far away from pi over 2, right? And that's confirmed by the results. Now, in the even sector, since there is no counter effect, the electrons are prey to whatever potential is applied, and therefore the phase shift changes a lot.
Okay, very interesting. So you have in the Coulomb regime, you have that for free. So
yeah, that's right, exactly.
Very good.
right.
Thank
And
you.
that's the origin of the singularity before you apply the potential, right? It's just this difference of pi over 2.
Okay.
Okay.
Thank you.
Okay. Well, thank you for a very nice question.
I have a question. I have a couple of questions. I'm curious about something you mentioned, that the BTN that got the result, wrong result. Isn't the BTN that exact? So how come they? Yeah.
Okay. Yeah, that to some extent remains a mystery, but we have a guess, right? The beta ansatz, you have to start out somewhere, right? And apparently they're starting out in the wrong sector, right? They're starting out the even sector.
Okay.
And so the calculation is exact in the even sector, but it's not looking at the odd sector. Right?
Okay.
Right.
My other question is, all the calculations you did are for a flat band, right?
Yes, right.
Does anything change if you have any singularities nearby, or that doesn't matter? Let's say everything that you see is robust against having Van Hove singularities or things like that nearby.
Yeah, okay. If you have a singularity near the Fermi level, right, within the threshold region, then that I think would be a problem, right? But if it's away, right, normally the singularities will be close to the band edge, not to the Fermi level, right? And then there's no problem. It's robust, I guess. Yeah.
Okay. And if there are no other questions, yeah, I have one more question. Did you? I noticed that you showed 3 points on the phase diagram where you showed results A, B, and C. Did you do any calculation exactly on top of the line, the phase transition line?
Okay, excellent question. But it's very, very difficult to do that numerically, right? Because you don't know where that line will
Where
be to
exactly?
calculate numerically, right? And then if you're off by 10 to the minus 9g, well, not 10 minus g, you cannot reach with a computer, right? But if you're off by 10 to the minus 10, then you're off, and that's it, right? There's nothing you can do about that, right? You can get closer and closer, but nothing special happens because this is a first order phase transition.
Okay.
Right? So getting closer doesn't help you, right?
Okay.
You have to be very lucky and to be right on top. So that we cannot do. Right?
Okay.
Numerically. Okay. Right. That's good.
Any other questions? I don't see any.
Pedro Orellana has a question.
Yeah.
Yeah, go ahead.
Very nice talk, Luis.
Thank you.
My question is, this BIC is only one BIC, or we have a BIC for high energies?
No. There will be only one BIC here, right? You're going from the bonding or anti-bonding orbital having 1 electron to the anti-bonding orbital having 2 electrons or 0 electrons, right? You can go either way, but that's so you're talking about the anti-bonding orbital. The anti-bonding orbital is what defines the BIC, right? If you think of suppose that it was not coupled at all, there's no coupling between the dots and the conduction band, then you'd still have the BIC with a single electron, or 2 electrons, or with 0 electrons, and then you'd have two very sharp lines that you could define, right? From the ground state to the first excited level, and from the ground state to the second excited level of the antibonding level. Right? So this is what defines the BIC. Higher up in energy, you won't have anything.
Okay, thank you, Luiz.
Right? Okay, thank you.
So it appears that we don't have any other questions. Werneck, anything? No?
Yeah, I do have a comment.
Okay.
So your calculation was done with NRG, right? So
Yeah.
So I was wondering, since the potential you apply in the conduction band will affect more dramatically one sector other than the other. So I was wondering if you had some sort of interaction in the conduction band, this scenario could be a little different. But then to treat with the NRG would be more complicated. But can you tell anything about that?
Well, if you have, you mean you've had electron-electron interactions in conduction?
It's small interaction. It's small interaction. But...
Yeah, well, that if you have electron-electron interactions, those tend to be renormalized at low energy, right? So I don't think they'll have any qualitative effect, right? What you could have is perhaps a non-uniform density of states, but these things will only introduce irrelevant operators, right? So they won't, they definitely will not affect the calculation, right? So I don't expect anything like that to spoil the results. Now, one thing that's very important, and I failed to mention, in fact, right, it's very important that the two dots be identical, right? If they're not identical, you lose the symmetry, and then everything else is washed out, right? So they have to be identical, right? So from the experimentalist viewpoint, that's a big problem, right? Because to have two dots with the same U is extremely difficult. Right? The couplings you can adjust, but the Coulomb repulsion is quite another story.
Can you maybe do some experimental setup where you are not using quantum dots, you are using real atoms, because then you can have honest to God equal.
That's a good idea. In fact, this project originally started with an idea that Ciridonio had, that we could have atoms coupled to graphene. And then we moved over to the quantum wire because it's easier to carry out the calculations. But maybe we should go back to the original idea. Right? You have a very good point there.
The point there, perhaps, the point there is in the atoms, you should be perhaps not easy to get them coupled symmetrically with the same amplitude.
You lose.
Okay, but that you can adjust, right? If you have just asymmetric couplings, you can still redefine your orbitals to have an equivalent combination.
That's right. That's right.
Yeah, so that's possible, right?
So the transformation would not be very clean like that, but you have some extra.
Exactly. Exactly. Yeah, very well put. That's exactly the way to describe it. Okay.
So if we don't have any other questions, let's just thank the speaker again. Thank you very much for the very nice result. I will be sending you an email soon, today